All right, here we go again. This is 15.2. We're talking about alloys today. Just before we get stuck into the alloys proper, let's think about metal structure. This would be topic 3, paper 1, structure and bonding. So when we think about a metal structure, if it's a pure metal that is, we imagine the metal atoms organized in neat rows and columns. We talk about a regular structure or a lattice there. A lattice is just a repeated mathematical arrangement. So we've got a mathematical pattern, and it goes on for millions and millions of atoms. So that's a lattice. The metals are good at giving away electrons. So we imagine that the electrons from each metal atom are sort of released into the lattice, and they would just be dotted around all over the place. So they become delocalized. And because each of the atoms has lost electrons, they'll all be positive. So we have positive metal ions surrounded by delocalized electrons. Sometimes you'll hear books talking about a sea of electrons, like you've got boats moored in the water and the water is able to sort of flow around the boats. It's not a bad image because, of course, the electrons are able to flow around. That's why we use the word delocalized. In other words, they don't have a particular location. They don't have a particular local area. Let's just remind ourselves about some metal properties then. Metals have a high melting point. Iron is about 1500 degrees. It's pretty high. Why is that? Well, because those ionic bonds, the forces between the metal ions and the delocalized electrons are strong. Whenever anything has a high melting point, there must be some strong forces that are being broken. And they require a lot of energy to break. Another important property of metals, well, they conduct electricity when solid. Why is that? Well, those delocalized electrons can move through the structure. What does that mean? Through the structure and carry charge. It means that we're talking about electrons going somewhere. If I focus on this electron here, it's not just kind of going around in circles, it's on its way somewhere through the metal. So we imagine the electrons moving in a particular direction through the structure, and as they do so, carry charge. Remember, current of electricity is the movement of charged particles. And lastly, we think about metals being malleable. That means that if we hammer them or roll them, we can change their shape fairly easily. Metals usually flatten or bend. They tend not to shatter, like, I don't know, plastic wood or wood. So we say they're malleable. So what's that about then? Well, you can imagine that if I hit my layer of atoms here with a force, that whole layer would be able to slide over the top of the others. So the atoms are in layers which can slide over one another. Okay, the atoms are in layers which can slide over one another. That's all just a bit of recapping. when we think about alloys, one of the things that makes alloys beneficial is they're usually harder. And the reason for that is if I've got my regular metal structure and then I suddenly introduce an atom which is different and has a different size, then what that does is it disrupts the lattice. So we end up with a, sort of strange looking bit of the lattice like that. So the different sized atoms disrupt the lattice, and that means that the layers can no longer move or slide over each other. So by introducing a different type of metal, usually, into the element, we get an alloy. So some important alloys that you should be aware of. So first of all, copper. You're probably aware that if you have copper and zinc together, that makes brass. Brass is used for fairly ordinary household products like the taps in your bathroom, maybe. Door handles, door knockers. Things that need to be hard. They're not going to wear out, and so on. And then if I add copper to tin, that makes bronze. Used, of course, famously by Neolithic people 10,000 years ago to make axe heads and shields and swords in the Bronze Age. A bit less now, because we got the Iron Age. We have a much more robust material, but it's still used to make statues and probably some other things around the house. And again, one of the main reasons we like brass and bronze is it's harder than pure copper. Copper's actually quite a soft metal when it's on its own. Aluminium makes a good alloy because it's a very lightweight metal, but not super strong. So if we combine it with other light metals, so a common one is titanium. It's another strong lightweight metal. We've then got a mixture, so we have a harder alloy but still lightweight. That can be used to make aircraft bodies. Some car bodies are made of aluminium alloys, some Audi bodies. Also, of course, bikes. The high-end bikes tend to be made out of carbon fibre, but reasonably good bikes in sort of 600 to 1,200 pounds kind of range are often made of aluminium frames or an aluminium alloy frame because they're much lighter. Obviously, lighter bike makes you go faster for the same amount of force, but the physics. Gold. So when we look at things like a gold ring, that's almost always a gold alloy. You might have seen the old movies where a Western guy gets a gold coin and he bites into it. What he's looking for there is if he can't bite into it, it's probably not gold. Gold is a soft material, which you could definitely bite into. So if it's pure gold, it'll be soft. If you've got a wedding ring on, you don't really want it to be soft. I want that wedding ring to last me years, decades, whatever it is, the rest of my life. So we need a harder material. When we mix gold with other metals, we talk about carats. That's not like the orange root vegetable. It's spelled differently, and a carat is a 24 carat gold is 100% pure gold. So if I had, say, 16 karat gold, well, 16 over 24, that's 2/3, so that would be 67% gold and 33% something else. Usually gold is alloyed with silver, which of course is another very unreactive metal. If you're making a gold ring, you want it to be super, super hard. So actually gold rings are only 9 karat gold. Most of the rest is silver. That produces gold that is so pale it doesn't look like gold anymore. So they have to add a bit of copper to make it gold coloured. So actually a gold ring is only about 1/3 gold. Most of the rest is silver and then a little bit of copper. But that gives you a really hard material. It's also not super expensive, so we can afford our gold rings for our weddings. The last material I want to talk about today is steel. Steel is mostly iron with a tiny amount of carbon. Carbon's quite unusual in that it's a non-metal. So steel's one of the only alloys that's made of a metal and a non-metal. All of these other ones are mixtures of different metals, but carbon's a non-metal. It works in the same way in that the different sized atoms disrupt the lattice and make the metal harder. We're talking very small amounts of carbon here. So all steel contains some carbon. Low carbon steels, and by low carbon I mean less than 0.25%. Low carbon steels are relatively soft. So if you're making something like a car body, you actually want the material to be fairly soft. You think about a car body, think about a car door. If you kicked a car door, it would probably bend. The owner of the car would not thank you for that, but it's relatively soft, yeah? And of course, we want car bodies to be relatively soft because that means when you crash, the steel will crumple, and that crumple zone, that is the protection around you, that absorbs the energy of the collision and stops you from being injured or worse. So we want nice soft metals, and of course it's also easy to roll and make into the car body as well. So car bodies and some other sort of soft steel materials, flexible panels, for example, on the sides of buildings, will be made of low carbon steels. High carbon, which is really only above about 2.5%, would make a much harder steel. So this is what's used for your tools, your drill bits, your nails, your saw, your kitchen knives are usually made of high carbon steel. They can be sharpened to a very high degree of sharpness. They cut very effectively. Of course, the disadvantage of having a harder steel is that it also becomes brittle. So I don't know if you've ever had this unfortunate incident where you're working with a drill bit, narrow drill bit, and as you're drilling, the drill bit snaps in the wood or whatever it is you're drilling into. That's because the drills are made of high carbon steel and therefore they're more brittle. You can also, if you've got a nice kitchen knife, get it at the wrong angle, you can snap that, believe it or not. So soft means it can be damaged easily but absorbs energy, so that's your low carbon steel. High carbon steel, harder, yes, but unfortunately more brittle. And the last type of steel I want to mention, and again this goes back to the resisting corrosion from the last lesson, or resisting rusting, is your stainless steel. So stainless steel contains carbon, but it also contains other metals like chromium and nickel, metals that tend to resist corrosion. And most stainless steel, as the name suggests, stainless means that it doesn't get those sort of nasty rust patches on it when it gets a bit wet. So stainless steel might be used for example, the spokes on a bike, or the rims are sometimes made of stainless steel. If you've got alloy wheels, we actually talk about alloys, don't you? Rather than having sort of nasty old hubcaps, you get alloy wheels. Those are steel. They actually mix in a bit of magnesium into that to make it corrosion resistant. So they withstand corrosion. Also tend to withstand higher temperatures, pressures, more extreme conditions. So engine parts, cogs, reaction containers. If you're making your ammonia, as we will be talking about later in this topic, making ammonia, you need a container that's not going to corrode at high pressures, high temperatures. So stainless steel works very good for that. It's also used in things like industrial kitchens, or big canteen kitchens, or proper chef's kitchens. Make everything out of stainless steel. It's easy to clean. It's not going to corrode, and it's obviously looks nice and shiny. Okay, that's it. 15.2 done.